Geology. I can't think of anything to rhyme with it, so we'll just move on. There we go. All right, so now we're going to look at evolution from a geologic standpoint and geologic time. Starting with James Hutton back 1726. He lived, born 1726, died 1797. And who James Hutton was a geologist. And a geologist is someone who studies rocks and the Earth's processes. And what he proposed was this theory of gradualism. This theory tries to explain that the Earth has to be very, very old in order for processes to occur. So, such as mountain formation or canyon formation, it would require an enormous amount of time. So think about this, the theory of gradualism, that things are happening gradually. So if it's happening gradually in very short amounts, then it's going to take a huge amount of time for that to happen. So you have the young mountain appearance versus an old mountain appearance. So after hundreds of thousands of years of weathering and erosion, this is where we end up. So according to the theory, the Earth has to be very, very old. Now, this is very important to Darwin's theory of natural selection, because the theory of gradualism supports the time frame needed for natural selection to transform species over generations. So, I mean, obviously, it's going to take a long time. And so this concept of gradualism would support the, would go hand in hand with, Darwin's theory of natural selection. Now, another scientist that was instrumental for Darwin was Charles Lyell. And Lyell was born right when Hutton died, so 1797 to 1875. He was also a geologist, and he wrote a book titled Principles of Geology. And Darwin actually took this book on the HMS Beagle voyage with him. And so in the book, what Lyell proposed was this theory of uniformitarianism. So just think about this, uniformitarianism. So what the whole concept here is that the key to the past is the present. So understanding the past is looking at the present. Now, that's not always the reality. I mean, we know that, I'll go into a little more detail on that in a little bit. But that's the concept there. The key to the past is the present. So we look at what's going on in the present. We try to determine what happened in the past. So this theory tries to explain that the same geologic processes that are occurring today also occurred in the past. So the processes help to create over millions of years the geologic formations that we see today. So for an example, when we look at, so here we have new erosion on the side of a road. Okay, so we see that's new erosion happening. And this, the Grand Canyon in Arizona, is an example of millions of years of erosion. Now, does it have to be millions of years? No. I mean, we know that differing amounts, there's all kinds of events that could cause that erosion. But certainly it would make sense that if we're looking back here at this and we know how long it took for this to erode in our present day, since we can observe it, then we look here and we think, well, it must have taken, we can extrapolate and come up with the possibility that it clearly must be millions of years old. So very important to look at Cuvier's theory of catastrophism, and then working together with Hutton and Lyell, and this is where Darwin came up with his theory of natural selection. So he was influenced by these different scientists and their work, and that's where he got some of the concepts and put them all together. Again, looking at, here's a picture here of thunderstorms now. thunderstorms with rain now versus what possibly it could have looked like billions of years ago. So, you know, some differences there. All right, so now when we talk about using geology in order to try and date things, in order to try and come up with the dates on things. So we use fossils. And there's two ways that we can use fossils to try and date things, to come up with a geologic timeline. First one is absolute radiometric dating. So what this does is it uses the half-life of elements, of radioactive elements that accumulate in an organism over time. So over time, we have radioactive elements in us, and that can be tested for. So we look at that, the half-life over time. And what that is it continues in this case, in 1 year, or in one half-life, you're going to have half the amount of material that you started with. And then in that same amount, you're going to have a quarter. Each time you half the amount. So you can look at this, and long term, you can count the difference. You can look at the amount of parent isotopes versus daughter isotopes and make a comparison there and be able to determine relatively how old something is. We use C14, carbon 14 is used for if we want to look at something that is thousands of years old, and we use uranium-238 if we're trying to figure out millions to billions of years old. Now, I'm going to pull up some information for you and give that to you in class to show you the level of accuracy of those. Again, keep in mind, we're looking at this theory, what the scientists here, when they talk about millions and billions of years old, we don't have anything that can accurately measure those amounts of time. We just don't. But according to the theory of uniformitarianism, then we can look at what's going on in the present and extrapolate it out, which is what occurs with this. So we have this relative dating. So we can look at the fossil record and we can come up with relatively where they are found. And that's based on the strata or the location. Going back here, well, actually, let me go back here to this picture. You see these layers? We have all these layers, and we can see the layers. We see the layers that are there. And so what we do is we look at those different strata of rock and we index the fossils to try and come up with some kind of timeline. It would make sense that fossils that are down here are going to be older than fossils so the organisms that are fossilized down here are older than the organisms that are fossilized up here. I mean, it just makes sense. I mean, stuff deposits on the top. It's not going to deposit from the bottom up. And so when we look here, at this relative fossil dating, we use these index fossils. So this is the most recent. These are the things that we're going to find at the top. And we go down here and we find trilobites and things like that in these lower levels. So it's compared, so we use the index fossils to compare looking at the location or the strata where we find an unknown dated fossil. So if the unknown is found above the index, the unknown is younger. I mean, it just makes sense. If we found this, then we would say that this right here is younger than something we would find here. So, and if the unknown is found below it, then it's going to be older. So positions are relative to time. And it seems to make good sense. All right, the plate tectonics. This plate tectonics refers to the moving of the continental plates. So the continents are moving are a direct cause of the biogeography of the species. We look at collisions. When these plates collide, when they come into each other, then that's how mountains are forming. You have two separate plates that collide and they push up, and when they push up, it's forming a mountain. A separation, when two of these plates separate from each other, then we have sea floor spreading, and you could think about it like the world zipper in the Atlantic Ocean floor. So it just opens up. And then we have subduction and slipping, where we have plates that are being pushed under the other. So examples of that are in Japan, the plates are sliding past one another, like in California with the San Andreas Fault. So those plates, one will slip under the other. And then, of course, we have the ring of fire, which refers to the volcanoes all around the Pacific plate. And so, and that creates the volcanoes as a result of those. So here we have this when two plates come together, you're going to have mountains forming. When you have the when they pull apart from each other, then you have this opening, the sea floor spreading. And then you have subduction, where you can see one will form underneath another one. So it pushes underneath that one. Oh, wow, that's all we have. That's so sad. It's over for today. Bye-bye.